We have discussed how carboxylic acids can be converted into acid derivatives, and this includes acid chloride, acid anhydride, esters, and amides. An acid can also be reduced to an alcohol. So please go over all these three reactions. And next, we are going to discuss all these acid derivatives. Start with acid chloride. By reacting with thionyl chloride, a carboxylic acid is converted into acid chloride. Reacting with phosphorus tribromide, carboxylic acid is converted into acid bromide. As you can see in this chart, among all the acid derivatives, acid chloride or bromide are the most reactive, okay, because chloride or bromide are the best leaving groups, okay, and therefore by reacting with a carboxylate, for example, acetate, that's a acetate. This will attack carbonyl-carbon, leaving group leave, and you will get a acid anhydride. Okay, by reacting with a alcohol, so the alcohol will attack carbonyl-carbon, leaving group leave, you get a ester, right? By reacting with amine, okay, the nitrogen lone pair electron will attack carbonyl-carbon, chloride leave, and you get amide. So starting with acid chloride or bromide, you can prepare acid anhydride, esters, amide, so all the acid derivatives. Okay. Now hydride, on the other hand, so from lithium aluminum hydride, so the hydride will attack carbonyl-carbon twice because chlorine is a leaving group, and so that will give you alcohol. Okay, so hydride attack twice, and the Grignard reagent, okay, for example, metal group, that's Grignard reagent, and will attack twice. All right, so you got alcohol with two alkyl groups. Gilman reagent, on the other hand, will only attack once. Okay, and that will give you a ketone instead of an alcohol, like Grignard. So we're going to explain more in the next few slides. Acid chloride or bromide can also be hydrolyzed back into carboxylic acid. As you know, carboxylic acid can be converted into all the acid derivatives, and that the reverse is also true. Okay, acid chloride, bromide, or anhydride, or esters, amides, they all can be converted back into carboxylic acids by hydrolysis, and that is add water. In these slides, we show the general reaction mechanism of nucleophilic substitution reaction of alkyl halides. Okay, so a nucleophile here, such as hydride, Grignard reagent, water, alcohols, they will attack the carbonyl-carbon, forms a alkoxide, okay, and then the alkoxide reorganize, forms CO double bond, and at the same time the leaving group chloride leave or bromide leave, and that give you the product. So if the nucleophile is water, right, so the water adds to here but deprotonate, so the product will be a carboxylic acid, and that's hydrolyze. All right, hydrolysis of acid chloride. Oh, what? Now, if the nucleophile is alcohol, then the product will be an ester, for example, methoxide. So if it's amine, the product will be an amide. Okay, so R, H something, all right? Note that carboxylic acid, the OH has lone pair electron. Here, ester oxygen lone pair electron, nitrogen lone pair electron. This lone pair electron conjugate with the CO double bond. And so this conjugation makes the carbonyl carbon less reactive. Okay, and therefore, after first attack of these nucleophiles, the product carboxylic acid and esters and amides, they are the final product. There's no second attack. Okay, alcohol or amine, they don't attack twice. On the other hand, if the nucleophiles are hydride, for example, lithium aluminum hydride, or Grignard reagent, that's carbanion, all right, after first attack, for example, if it's hydride, after first attack, so the leaving group chloride left, and you get a aldehyde, okay? And there's no electron donating from the hydride, and therefore, this carbonyl carbon is still very reactive. And hydride is also very strong nucleophile, so this will attack twice, as shown here. So the second attack gives you a alkoxide which cannot reorganize because these are both hydrogen. There's no leaving group, and after protonation, you get an alcohol. Okay, so hydride will attack twice. Grignard reagent will attack also twice. So after first attack, you will get a alkyl group, for example, methyl group. All right, and then second attack, all right, you get two methyl groups, okay, with the alcohol. Okay, so the conclusion is nucleophile substitution, if nucleophile is water, alcohols, amines, the reaction will be the product of one attack by the nucleophiles, give you carboxylic acid, esters, amines. If it's Grignard reagent and hydride, it will attack twice, give you alcohol. This shows benzoyl chloride reduction by lithium aluminum hydride. Okay, so the hydride attack once, give you a alkoxide, which then reorganize from a CO double bond and leaving group leave, and you get aldehyde. Aldehyde is still very reactive. Hydride is very nucleophile, attack second time, give you alkoxide, protonation, final product is alcohol with two hydrogens added. It shows benzoyl chloride react with Grignard reagent. The carbanion will attack first time, give you a ketone. Okay, first you get a alkoxide, reorganize, leaving group leave, you get a ketone. And then the ketone is still very reactive, and so the powerful nucleophile carbanion attack twice, a alkoxide, and then a protonation give you alcohol with two methyl groups, okay, both from Grignard reagent. So the general reaction is acid chloride, two equivalent Grignard reagent give you a alcohol. Is a comparison of acid chloride react with lithium aluminum hydride and Grignard reagents, and both attack the nucleophile attack twice. Hydride attack once, hydride attack twice. Carbanion once and twice. Both give you alcohol with two alkyl groups or two hydrogen groups. Okay, so please pause and practice, see if you can draw these mechanisms. In chapter 10, we introduce different organometallic compounds, including Grignard reagent, Lydian reagent, Gilman reagents. And they have similar properties but also have differences. So in the last slides, we showed that acid chloride, okay, can react with Grignard reagent, for example, methyl magnesium bromide, and this carbanion will attack twice, right? Leaving group leave, and the end product is alcohol, okay, with two added alkyl groups, for example, methyl. On the other hand, if it's a Gilman reagent, all right, for example, dimethyl copper Lydian, the methyl group will attack only once. Okay, that's a very important difference between Grignard and Gilman reagent. Okay, and so you end up with a ketone. So, for example, this is metal, and that's a metal ketone. Note that the reaction generally carry out at very low temperature to keep low reactivity, so only attack once. All right. So if you want to make a ketone from acid chloride, you should choose Gilman reagents. Okay, you should choose diorganol copper Lydian reagent. Do not use Grignard, because that will give you an alcohol. Here shows an example of acid chloride react with Gilman reagent, okay, diethyl copper Lydian. So the carbanion ethyl group will attack carbonyl carbon once, replace chlorine, give you a ketone. Okay, please note that the reaction acid chloride react with Gilman reagent is unique for acid chloride. All right, it doesn't apply to other carboxylic acid derivatives, including carboxylic acid itself, esters, acid anhydride, amides. As I mentioned before, all the acid derivatives can be hydrolyzed back into carboxylic acid. Okay, for acid chloride, the hydrolysis requires base to remove hydrochloric acid produced during the reaction. Okay, we'll show mechanism next. Here shows the mechanism of hydrolysis of acid chloride. First, water has lone pair electron, serves as a nucleophile which attacks the carbonyl carbon, and it forms a oxide. Okay, and the oxygen oxide will reorganize from a CO double bond. At the same time, will expel the leaving group chlorine. Okay, and the oxygen ion hydrogen has two hydrogen, so one will be deprotonated, and that gives you a neutral product. That's carboxylic acid, and it is this step, okay, to deprotonate the hydrogen requires base. Okay, the base usually we can use pyridine as a solvent and also a base. In the last slides, we showed acid chloride react with water to form carboxylic acid. The reaction is called hydrolysis. Okay, acid chloride also react with alcohol or amine, and the reaction are called alcoholysis and aminolysis. Okay, the reaction mechanism follow the same pattern. For example, if it's alcohol, such as methanol. So CH3OH. Okay, so the lone pair electron here, all right, from alcohol will attack carbonyl carbon, forms alkoxide, that's the alkoxide, and then reorganize, forms a CO double bond, expel chlorine, and then deprotonate by a base, which usually is a pyridine, and that give you a ester, right? So alcoholysis give you ester. Okay. Now, if the nucleophile is amine, all right, it will attack from alkoxide, reorganize, expel chlorine, deprotonation, all right, give you amide. Okay, here instead of pyridine, we can use twice amine. Okay, so you can use two equivalent amine. So one is as a reactant, one as a deprotonation agent. Okay, and that will also give you the amide. Here shows two examples of alcoholysis. Acid chloride, alcohol, okay, so that will attack leaving group leave, you get ester. And here another acid chloride, alcohol, attack leaving group leave, you get ester. Here shows two examples of aminolysis. Okay, so acid chloride react with amine. So the amine, in this case, is ammonia, attack carbonyl carbon, right? Leaving group leave, and another equivalent is to deprotonate hydrogen, and that give you amine. Okay, so instead of use pyridine, here we use more ammonia. Two equivalent ammonias. So one is reactants, one equivalent is reactants, another as a base. Okay. Similarly, here acid chloride and amine here is dimethylamine. All right. So one equivalent attack, the other one is used to deprotonate, and you get NN dimethyl benzamide, okay, dimethyl benzamide. Note that in both cases we use two equivalent amount of amines. Okay, one is used to neutralize the hydrogen chloride, because there's one step you need to deprotonate the hydrogen. Last two examples, we use two equivalent amine. One used as a reactant, the other as a base to deprotonate hydrogen. Now, if amines are very expensive, if you are using a very expensive amine, for example, in this case, this one, you don't want to use two equivalents, and so then you have to add a cheap base, in this case sodium hydroxide. So one equivalent amine serves as a nucleophile, attack carbonyl carbon, and that give you the desired product. And during the reaction you need to use a base, in this case is hydroxide. Acid chloride is most reactive acid derivative. So we have shown that it can be used to make amides, esters, and how do you make acid anhydride? So this is an anhydride. One is acetic acid, one is formic acid. So these two combine forms anhydride. So how do you make this one? All right, we can use acid chloride. So one part is acid chloride, the other part is carboxylate. So here we can use acidic acetyl chloride, and the other one is formate. All right. So this comes from formic acid. So formic acid, here is a formic acid. When you add the sodium hydroxide, acid-base reaction, so it deprotonate hydrogen and the hydroxide, right? It's an acid-base reaction, and that will give you acid formate. It's a anion. That's the formate, anion. And this is a nucleophile. So this nucleophile will attack carbonyl-carbon, leaving group leave. You get a anhydride. Okay, and that's also a very general way, general method to make anhydride. Okay, so one part is come from acid chloride, the other part come from acid carboxylate. Summary of acid halides reactions. Acid halides are the most reactive acid derivatives. Okay, acid chloride or bromide can be converted into acid anhydride by reacting with carboxylate, as we shown in the last slides. By reacting with alcohols, it can be converted to esters. By reacting with amines, we can produce amides. Okay? By reacting with water, it hydrolyzes into carboxylic acid, go back to carboxylic acids. Okay? And it can be reduced by reacting with lithium aluminum hydride, so the hydride will attack twice and give you an alcohol. Grignard reagent attack twice, give you also an alcohol. All right. On the other hand, Gilman reagent attack only once, and that give you a ketone. We have discussed the chemistry of acid halides, right? Acid chloride or bromide. So these chloride bromide are very good leaving group, and they undergo nucleophilic substitution reactions. Okay, now the chemistry of acid anhydride is very similar to the chemistry of acid halides. A acid anhydride is a molecule with two carboxylic acid combined by losing a water molecule. So one of the carboxylate serves as a leaving group. Okay, and because of the similarity of the chemistry between acid anhydride and acid chloride, we're not going to spend as much time to discuss the reactions, but just give you a summary. If a nucleophile, okay, here, will attack one of the carbonyl carbon of acid anhydride, forms a carboxide, which will reorganize from CO double bond and expel one of the carboxylate. All right, so that's a product by nucleophilic substitution once. All right, this nucleophile can be water. All right, and then that's hydrolysis, and the product is carboxylic acid. So if the nucleophile is a alcohol, such as CH3OH, methanol, the product will be ester, right? If the nucleophile is amine, and let's say ammonia, and the product will be amide. Right. So all these nucleophiles attack once, just like in the case of acid halides, right? Because you see the lone pair electron, they conjugate, and so the carbonyl carbon is not as reactive. And also these nucleophiles are weak nucleophiles. Now, if the nucleophile is a lithium aluminum hydride or a Grignard reagent, and they will attack twice, and so the product will be a alcohol. Okay, just like acid chloride or bromide. So you can see almost all reactions are same, almost the same, follow the same pattern. All right, there's some differences. For example, Gilman reagent will not react with acid anhydride. In summary, acid anhydride is the second most reactive acid derivatives next to the acid chloride. Okay, by hydrolysis, can react with water, it go back to carboxylic acid. By alcoholysis, can react with alcohol, it goes to ester. Aminolysis, can react with amines, it gives you amide. By reduction with lithium aluminum hydride, it gives you alcohol. By reacting with Grignard reagent, it also gives you an alcohol, but with two alkyl groups. Here shows two examples of acid anhydride reactions. One is aspirin synthesis, and this reaction uses acidic anhydride. Okay, react with salicylic acid. So the hydroxide oxygen, okay, attack carbonyl carbon and expel a acetate, and that give you an ester. Okay, that's a aspirin. The synthesis of Tylenol also use acidic anhydride. Okay, with perohydroxyaniline. So here the amine, okay, react with carbonyl carbon, expel acetate, and that give you an amide. Problem 21.3. Show the mechanism of the following nucleophilic acyl substitution reaction. So here is acid chloride, and the nucleophile is methoxide in alcohol, okay, methanol. Alkoxide is much stronger nucleophile than alcohol itself because it has a negative charge, and therefore it attacks carbonyl carbon. Okay, so it's a alcoholysis reaction. It gives you ester. So the mechanism is the nucleophile attack carbonyl carbon, form alkoxide. Okay, that's alkoxide, and reorganize, go back to CO double bond, and expel leaving group, and that give you ester. Rank the compounds in each of following sets in order of their reactivity toward the nucleophilic acyl substitution. All right, so that is, you have carboxylic ester, carboxylic derivative. All right, so derivative, let's say it's X. Okay, and a nucleophile, okay, attack this one, leaving group leave, and that's called a nucleophilic acyl substitution reaction. The reason for the reaction is the polar bond. So oxygen is negative, carbon is positive. The more positive the carbon, the more reactive. Okay, so for A, you only need to look at the reactivity chart in the textbook or my lecture notes. You will see chloride is the most reactive, and then ester is, or then anhydride, right? And then ester, and then amide. So the rank is 1, 2, 3. Okay. Next one, if you look at the functional group, they are all esters. Ester, ester, ester. All right. So they are all ester. However, the difference is the last one has fluorine. Okay, 3 fluorine, and the second one has 3 chlorine. So as we know, fluorine is the most electron negative. That means it takes electron away, all right? And that will, when you have electron withdrawing fluorine, it will make carbon more positive. And if this is more positive, then it is more reactive. So the last one should be the most reactive. And then the second one is the second reactive because it has chlorine. And then the first one is the least reactive. All right, and this kind of effect is called the inductive effect. The electron withdrawing group take electron away through the chemical bonds, called inductive effect. Predict the products of the following nucleophilic acyl substitution reaction. In A, reaction between ester, here is ester, okay, that's the leaving group, and water under basic condition, okay? So that's a hydrolysis reaction, right? So the reaction, hydrolysis reaction for all the acid derivative will give you, go back to carboxylic acid. However, under basic condition, the acid will react with the base. So the final product should be a sodium salt, okay? The sodium is a cation that replaces hydrogen, right? That's acid base. Now, if the condition, the hydrolysis is is catalyzed by hydronium acid, so acid can also catalyze this hydrolysis reaction. Then the product will be the carboxylic acid. Now, in B, it's a acid chloride. Okay, the chloride is a very good leaving group, and the nucleophile is amine. So the amine attack carbonyl carbon and the leaving group leave. Aminolysis. So the product is amide. Okay. Next one is acid anhydride. Okay. So you have two carboxylate combined. And the nucleophile here is a methoxide. Okay, it will attack one of the carbonyl carbon, and the rest is the leaving group. It's a carboxylate as a leaving group. So what's the product? It's the ester, right? So this comes from methoxide, and this is the anhydride part. Okay, next one, the last one is thioester. Now, thioester is very similar to ester. Okay, oxygen and sulfur, they are very similar. So this is aminolysis again. So amine attack carbonyl and thio as a leaving group, and you get amide. How might you prepare the following esters from corresponding acid? Okay, so let's look at the first one, and it's ester, right? And this carbonyl compound, so this should be the acid part, and this should be the alcohol part. All right, so you have carboxylic acid, you have alcohol. Right, that's the Fischer esterification reaction. Okay, and therefore the first one should be 2-carbon acid, which is acetic acid, and 4-carbon alcohol, which is butanol. All right. Now let's look at B. Again, CO double bond part is the acid part. Okay, so that will be 1, 2, 3, 4 butanoic acid. All right. And this alcohol is methanol. Okay, so the methanol butanoic acid. The last one, carbonyl part is the acid. So that's the acid. All right, and alcohol should be isopropanol. All right, so this is the alcohol, and this is the carboxylic acid. If the following molecule is treated with acid catalyst, intramolecular esterification reaction occurs. So let's first draw this molecule. Okay, and the red one is oxygen, so carbon oxygen double bond with OH, and then CH2, 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 and then OH. Okay, all right. Now, so this molecule contains a carboxylic group, okay, and also contains a alcohol part, so two functional group. And as we know, carboxylic acid, alcohol undergo Fischer esterification. So when you have an alcohol and acid, they will lose water to form ester. Now, because this molecule, one molecule contains both, so the reaction between these two functional groups is called intermolecular esterification. All right. So here is the reaction. That's the molecule. All right. You want to draw like this so that the carboxylic acid and the alcohol is closer. They are closer so that they can lose the water right under acid condition, lose a water and form an ester. So here is the ester. Okay, and this is a CO double bond here, and this oxygen go here, right? So this V, and that give you a ester. How might you prepare the following esters using nucleophilic acyl substitution reaction of an acid chloride? Okay, so ester can be prepared by Fischer esterification, or it can use acid chloride. Okay, so acid chloride is the most reactive derivative, acid derivative. So if you add alcohol, all right, so such as methanol, then okay, the alcoholysis, right, leaving group leave, and you get ester. Right, so that's how you use acid chloride to make ester. You can see here, carbonyl part comes from acid chloride, and this part comes from alcohol. All right, so let's look at the first one. The first one, A, note CO2 means COO, right? That's CO2, CH3. So CO2 indicates it's ester. Okay, as we just showed, the carbonyl is the acid part. So you have 3 carbon, and so the reactants must be CH3, CH2, chloride. All right, acid chloride part. And the methanol comes from alcohol part, methanol. Okay, and therefore the A is propanoyl chloride, 3 carbon chloride, and methanol. And don't forget base. You need a pyridine or any other base. If you remember, during the reaction, you need to deprotonate hydrogen. Otherwise, you form hydrogen chloride acid, which will prevent further reaction. The next one, CH3, CH2, okay, CH2, oh, sorry, CO2, that indicates it's ester. CO2, and then CH2, CH3, and there's a methyl group here, okay, and so this must come from, okay, acid chloride, okay, so you have 2 carbon, all right, and this comes from alcohol, okay, and therefore the reactants is acetyl chloride and ethanol, and don't forget pyridine as a base. Okay, last one, ethyl benzoate. Okay, note O8 means it's ester. That's ester ending. And when you name ester, you name alcohol part first. It's ethyl, so that means CH2, CH3, right? And then you name acid. Acid is benzoic acid. So, all right. So that's the structure of ethyl benzoate. All right, and this should be prepared by a acid chloride and alcohol. So apparently this comes from acid chloride and this comes from alcohol. Okay, so it's benzoyl chloride and ethanol with purity. Which method would you choose if you want to prepare cyclohexylbenzoate? Okay, so two methods: Fischer esterification or reaction of acid chloride with an alcohol. So first, Fischer esterification is the reaction between a carboxylic acid and an alcohol. So usually we will reflux the alcohol. Okay, so this reaction usually limits to simple alcohols. Okay, because you need to reflux, right? So you need to require excess amount of alcohol to reflux. Okay, now if the alcohol has a very high boiling point, all right, then this reaction is not preferable, right? And therefore, a better way will be to use acid chloride and so acid chloride and alcohol. Okay, and in this case, we want to make cyclohexylbenzoate, right? We want to do that, and this comes from acid, so that's benzoic acid, and this comes from alcohol. So alcohol is a cyclohexanol. Cyclohexanol has a boiling point 160, and so it's not easier to reflux for high boiling point, and therefore Fischer esterification is not preferred. And the better way, instead of carboxylic acid, we use chloride, okay, benzoyl chloride, and this will be much easier. You don't need to reflux. It's attack here, leaving group leave. Okay, if you use benzoic acid, okay, with this alcohol under Fischer esterification, you need an acid catalyst and you need a reflux. All right, and because of the high boiling point, and it's not as good as this method. Chloride is a very good leaving group, and you don't need to high temperature. Mechanism of the following reaction. So this reaction is between a acid chloride and amine, okay, and the reaction is aminolysis. You get ester. Amide. You get amide. So what happens is amine is a nucleophile, attack carbonyl carbon, and eventually chlorine will leave, and deprotonation, protonation, you get amide. So here is the detailed mechanism. First, the amine nucleophile attack carbonyl carbon, give you a coxide, okay? So that's the coxide, and then nitrogen becomes positive charge because you have four bonds. It will be deprotonated, becomes neutral. Here amine becomes neutral, and then reorganize. Oxygen come back, form a CO double bond, and chlorine leave. Okay, expel chlorine, and you get CO double bond, and that's the amide. How could you prepare the following amides using an acid chloride, and amine? All right, so let's look at what happens between acid chloride and an amine, let's say methylamine. Okay, so this is, as we mentioned, acid chloride is the most reactive acid derivative. Amine will attack carbon near carbon, and leaving group leave, so you get amide. This is a simplified mechanism, not the detailed mechanism. Okay, and note that the part contains CO double bond come from acid chloride, all right, and the nitrogen part come from amine, all right, and therefore let's look at the first molecule. Okay, first molecule, note the CO means the CO double bond. Okay, so the first molecule is a CO double bond with NHCH3 and then CH2, CH3. Okay, so these come from acid chloride, 3 carbon, so that's a propanoic acid or propanoyl chloride, and this is a methylamine. And also remember, you need to add a base. Okay, you either add 2 equivalent amine or add a cheaper base, because the reaction generates hydrogen chloride acid, so you need to deprotonate. Next one, NN diethylbenzamide. Okay, so it's an amide. That means you have CO double bond with nitrogen. To name the amide, you first name the amino part, and here it says 2 substituents, NN diethyl, CH2CH3, CH2CH3, so 2 ethyl, and then you name the acid is benzoic acid, becomes benzamide. So benzoic acid. Okay. All right, so that's the NN diethylbenzamide. And to make this one, you need the acid chloride. So this is acid chloride. It's a benzoyl chloride. And this is the amine, diethylamine. So here is the reactants. Okay. Note that we need a base, inexpensive base, to deprotonate, react with hydrochloric acid produced during the reaction. Okay. Last one is propanamide. So you have CON. Now because there's no substituents on the nitrogen, okay, it's a propanamide, and therefore you just NH2. And propanamide comes from propanoic acid, so you have 3 carbon. Right? This this can be prepared by propanoyl chloride with ammonia. Okay, so propanoyl chloride with ammonia. Because ammonia is very inexpensive, so you can add 2 equivalent instead of adding other base. So one ammonia serve as reactants, the other serve as a base. How could you prepare the following ketones by reaction with an acid chloride and a lithium diorganol copper? Okay, first let's review the reaction between acid chloride. Let's say here, acid chloride with a Gilman reagent, let's say dimethyl copper lithium. So what happens is the carbanion attack carbonyl, leaving group leave, and you get a ketone metal. So this metal comes from the Gilman reagent, and the left side comes from acid chloride. Okay. Now remember, if it's green out reagent, it will attack twice. So it's very unique between acid chloride and the Gilman reagent. Okay, all right. Now let's look at the first molecule. So the first molecule has a benzene with CO double bond with a carbon hydrogen with CH3CH3. So basically, it's isopropyl. Okay, so based on the reaction between acid chloride and Gilman reagent, we can see that there are two possibilities. One is this is come from acid chloride, and this is a Gilman reagent. Okay, so that's one possibility. Let's see here. All right, so here is a possible benzoyl chloride, that's the acid chloride, and the Gilman reagent is diisopropyl. So this is isopropyl, one of them react. So diisopropyl couple Lydian, okay? Or this part can come from acid chloride, okay? And this benzene come from Gilman reagent, okay? So therefore, you have a diphenyl couple Lydian that's come from Gilman, and the whole right side, this one is acid chloride, and so that's the acid chloride. Okay, two possibilities, both will give you the ketone. Next molecule, okay, let's draw the molecule. CO double bond. Here you have CH double bond CH2. All right, CH2, CH2, CH3. Okay, all right. So again, ketone can be made by acid chloride and a Gilman reagent, and therefore two possibilities. This come from acid chloride, and this come from Gilman reagent. Okay, and so here you can see that's this part. So this acid chloride, all right, and the left side vinyl. Okay, that's this part is a Gilman reagent, or these can come from acid chloride, and so that's this one, and then this come from Gilman reagent. So you have dipropyl, all right, dipropyl copper Lydian. The mechanism of the following reaction, and this is between peryl hydroxyaniline, all right, and acetic anhydride. Okay, so as we know, acetic anhydride is second most reactive derivative, acid derivative, next to chloride, and you have two carboxyl come from two carboxylic acid by losing a water. One part can serve as a leaving group, and here the left molecule has an amino group, and that's a nucleophile. So the nucleophile will attack one of the carbonyl carbon, okay, and it will first form a carboxyl, and then a carboxyl reorganize, kick out the other acetate, all right, and that will give you an amide. Okay, so let's look at the detailed mechanism next. So here is the detailed mechanism. Here is the nucleophile amine attack carbonyl carbon, all right, give you a carboxyl, and nitrogen becomes ammonium salt, and one of the hydrogen can be deprotonated from a neutral nitrogen, and then a carboxyl reorganize from CO double bond. At the same time, it will expel the acetate. Okay, so and that will give you the amide. product would you expect from reaction of one equivalent methanol and the cyclic anhydride? All right, so first let's look at a reaction between alcohol and anhydride. Anhydride is a CO double bond with oxygen with another CO double bond. Okay, so this comes from this comes from two acetic acid lose a water, right? And so when they react, one part is served as a leaving group. So for example, let's say you have a alcohol, let's say CH3OH, and alcohol will attack carbonyl carbon, and this acetate is a leaving group, and so that gives you ester. Right, so this ester. Now what happens to this part, the leaving group? The leaving group is acetate, will protonate and give you acetic acid, OH. Okay, so you end up with a acid and a ester. Okay, if alcohol react with anhydride, one part becomes ester. Okay, this is ester. And this part becomes acid. The leaving group becomes an carboxylic acid. Okay, so that happens in a regular anhydride. Now let's look at this question. This is a cyclic anhydride. So that's this one. All right, that's anhydride, but inside a same molecule. Okay, same molecule. So what happens is the methanol, again, so let's see here, that's a methanol. It again attack one of the carbonyl carbon, and then this part, okay, will leave, but it's still in the same molecule. So what happens is you get this one. The top one becomes a ester, okay, and the other part becomes carboxylic acid. Okay, so that's what happens. All right, one is ester, one is carboxylic acid right here.